Very happy to have Matias Valdenegro here in this tutorial. I will present Matias. Is a researcher at the robot learning team at the German Research Center for the Artificial Intelligence in Bremen, Germany. He received his PhD in electrical engineering from Heriot-Watt University in 2019 with a thesis on detecting marine debris in sonar images. MCS in autonomous system from Bonn Rhein-Sieg University of Applied Science in 2014, and his computer engineering degree from Universidad Tecnológica Metropolitana in 2009. Matias participates in the organization of LatinX in AA series of workshops being visa share for the Europe IPS 2019 workshop and program committee co-chair for the LatinX in CVPR 2021 workshop. He also participates as mentor in Black in AA academic program and advisor mentor in the LatinX in AA mentoring program. Matias has published over 40 publications and reviews for top machine learning and robotics, conferences, and journals. His research interests include robot perception, reinforcement learning, uncertainty in machine learning, and their applications to robotics. It's an honor to have you in this tutorial. Thank you, Matias.
Thank you, Dania. So yeah, I will start. So the title of this tutorial is about how to write computer vision papers, but from the perspective of the reviewer. Because of course we write papers for computer vision conferences, but usually we do it kind of for ourselves. But the idea to get a high quality paper that can be easily accepted to any conference is that the paper is not only written for yourself or for the authors, but also for the reviewers and for the general public or for the general audience that should read the paper. So that's the important takeaway from this tutorial / talk. So let me start with kind of a thought-provoking sentence. Why do we write papers? Why do we write scientific papers? So of course, different people may have different ideas or motivations on why they write papers. So some people do it to advance their personal careers. For example, they're required if they want to apply for a graduate school or for a master's or PhD program. In many cases, it's slightly necessary or it's advantageous to have previous publications to show research potential. Or if they're doing a PhD, well, as a requirement of most scientific PhD programs, you need to publish your research. That's the first, let's say, barrier that you have to earn a PhD. And I would say it's not a very difficult barrier, but still it is a barrier that some people cannot overcome. And of course, the idea of this tutorial is to help these people to actually write good papers that then should have no trouble getting accepted in a conference. So other people do it to make an impact in the field, and this is more like a long-term perspective, because of course the stage of one's career may change during our life. Like maybe at the beginning you're doing a PhD and you want to publish papers to earn your PhD, and after your PhD then you write papers just because it's fun for you, because you want to make an impact in the field or you want to advance the state of the art. So of course this changes over time. It doesn't have to be a single reason for your whole life. And the last reason is to communicate ideas and advance the state of the art. And this is, I think, the right reason why we should write papers, because we do scientific research. And the idea is that you do research, do experiments, and then you report these experiments to the community, and you do this through a scientific publication, which is usually a paper, but it can be more than a paper. It can be paper, for example, plus videos, supplementary material, blog posts, and all of this. All of them are similar to a paper, and they follow basically the same rules. Like, for example, there are these modern kind of digital paper platform, like for example, Distill or Gradient.pub, where you can write a paper, but it's not a PDF, but it's basically an interactive website. And that can also be a publication, for example, and it also advances the state of the art. But the very important thing is that the scientific community writes papers in order to communicate what they have done and why is it important and how it improves, let's say, our understanding of nature and the world. And this, of course, is done for all the fields. It is transversal to all scientific fields and even some non-scientific fields. Like, for example, the social sciences are not completely scientific, but still they try to follow the scientific methods when possible. And I mentioned that some disciplines are slightly non-scientific because, for example, you cannot reproduce results or you cannot reproduce experiments in some cases. For example, if you use in people, if you do experiments at long-term scales, for example, in space, like, for example, the Big Bang is a theory, but you cannot actually do an experiment to check if the Big Bang is true or not. You can maybe do simulations and all the stuff, but not a real experiment. So, as I mentioned, the main idea of writing scientific papers is to communicate ideas to an audience or to review other people's work. And I mentioned this reviewing other people's work because there are also summary papers where you basically put your knowledge after reading many papers in a field and try to summarize like what is the direction that the field is going. And this is also research. It's also important that not all papers are just about improving the state of the art or just getting a better benchmark, but also about advancing the field in general and looking at patterns, for example, at common mistakes in, like, for example, no one is tackling this problem, or all the methods have this issue with this data set, for example, or with this. And that's also important and that's also a reason for writing scientific papers. So the core idea of this slide is that a paper is written not for the author to read, but for other scientists to understand. And this is very, very important, that when you write a paper, you should always consider that you have an audience, like a scientific community, which may vary depending if you are submitting to a journal or to a specific journal, or you are submitting to a different conference. Like, for example, you don't write a computer vision paper the same way as a machine learning paper. Even if the underlying idea is the same, maybe the perspective is not the same. But in any case, you need to have the perspective of the audience in mind always. And here I got a very nice plot. You've probably seen it many times because this is a very popular figure made by Bill Freeman in 2014. I got it from this tutorial/talk, how to write a good CVPR summation. And it shows that what is the effect on your career in terms of impact, and varying different kinds of paper. Like, you have a bad paper, an okay paper, a pretty good paper, or a creative, original, good work. So you see if you have a bad paper, yeah, maybe you have a negative impact, but it's very small. Like, one important thing to mention as well is that writing papers, like, the quality of your papers will improve over time. Like, maybe your first paper is not as good as your second, and then your third. Maybe your 10th paper is much better than your first paper. And this is, of course, because people learn over time. And this is something not to forget. But this relationship is actually not even exponential, but it's highly nonlinear, because you say, okay, a pretty good paper has an impact, but it's not that big, it's positive. But if you have a creative, original, and good paper, it may have a huge impact in your career. Like, people will recognize you for maybe for 1 or 2 papers that you have published, even if you have published hundreds of papers, even if many of these papers are at top conferences. But the important thing is that to put time into create good research, and not only to do, let's say, good research, like do many experiments, validate your technique a lot, but also it needs to be written correctly, and, let's say, in a way that other people understand it. Like, you need to craft your figures and your tables carefully. You need to have a good narrative in the paper. So when other people read it, they get your idea immediately, like the idea that you have in your head. They will grasp it immediately, and then they will possibly agree, yeah, this paper is useful. But if you don't write, let's say, the paper correctly, or it's hard to read, for example, especially if you are not if English is your second language, it can be, of course, at the beginning difficult to write papers, or to put your idea into words. But of course, words are not the only way to present ideas or concepts. You can also use figures, tables, and other. And also, for example, if you have good graphical skills or creative skills, you can also use them in your papers. Like, if people see if you, for example, you're very good at drawing in paper, you can also do like a drawing in paper and put it in your paper. There's no issue with that. Even if you have some artistic skills, you can also use them for scientific research. Like there are researchers that also they have like a second side of their life, that they really like to draw and to make creative art, and they also apply this to the research and to the general field, and that's also very, very important for research. But the takeaway here is that it is super important to actually polish your papers and your research into a very good state as best as you can. And this, of course, involves time, because maybe your first paper, it took a very long time to write and to produce, maybe many revisions in between. But over time, you actually improve this technique, and then you don't make the same mistakes. And then this, of course, shortens the time that you need to write a paper. And then you have more time to actually maybe make better figures, do better experiments, and so on. So it's very important to put time into writing a good paper. And now connecting with the reviewing of papers, I put this Venn diagram saying that people have writing skills. Most people that also write papers also act as reviewers at journals and conferences. Like as your literature or your, let's say, published papers increase, you will probably get noticed by other people, and they will send you reviews for requests for reviews for journal papers, for conference papers, and so on. And then you will also start to act as a reviewer. And this is what happened to me, and what will happen for you, for example, during your PhD and after your PhD, because in many fields we are in a severe shortage of reviewers. But the nice thing is that there's a set of skills that it's common between writing and reviewing papers. And I think this intersection is actually quite large, much larger than I'm showing here. Because when you write a paper, you need to have the perspective of the reviewer, like what kind of questions the reviewer will ask. So if you review many papers, and also if you have very good reviewer training, because reviewing papers is, of course, not enough to be a good reviewer. But if you put time to do your reviews and you have a good style, this will transfer also into your own papers, because then you say, okay, if I write this sentence, the reviewer will think this. Okay, maybe if I change it, or if I put this figure, I'm showing this to the reviewer, and the reviewer will actually understand my idea, might be much easier. And also reviewing papers requires what I call the author's perspective, because of course, I reviewed papers for all the top conferences, for NeurIPS, for ICLR, ICML, and I always see that that many reviewers, they ask things that are maybe not that are probably too extreme. Like they say, yeah, maybe you should repeat your whole experiment on the ImageNet dataset, which requires a large infrastructure in terms of computation, and also code. Like you cannot just use a tutorial to write code for it to train a good image. Like you need to have specialized people to do this. And maybe by doing that, you actually don't get much scientific knowledge. So of course, the reviewer should also consider, okay, the authors already did a lot of work, and maybe there's enough for the paper to be accepted, or at least there's nothing to complain. A lot of the reviewers' perspective is that a lot of reviewers, they complain for every small detail maybe that the paper may have, but maybe that detail is not really relevant in terms of a scientific perspective. But of course, that's why I say these are kind of two sides of the same coin. But the difference is that this coin has a shared side, which are these common skills. So now I start with what we call the 7 Ws, which is kind of a conceptual framework of how to do scientific research. And this is, I think, 3 slides from now. And it basically decides how you should frame your problem. And the nice thing about these 7 Ws is that these are questions. And these are questions that you, as an author, should answer when you write the paper. And also, as a reviewer, we also use these questions to actually understand what is your research, and how does it frame with other people's research. So the first W is, what is the problem? And of course, here we need to define the problem and its context. And this is very important that, of course, if you read a paper at the beginning, they always mention what is the problem and why, to whom is it important. And that's the second W. Why is it important? You need to describe the problem in enough detail so other people understand it, and describe why the problem is important and to whom it is important. Because of course, maybe some problems are not important to some people, but they are important to some other communities. And this is very important to frame to whom it is important and why. And this is, of course, extremely important, because if you are working on a problem which is not important for anyone, then of course, what's the point? Maybe this is more difficult, for example, if you do basic science, but even if you do basic research in computer vision, you can still think, okay, if I solve this problem, maybe it has these potential applications. And this is one reason why a problem is important. And the next is what have other people done about the problem? That this is basically a survey of the state of the art for this specific problem. So you need to describe this in enough detail so actually people see that you actually are aware of like the context of your problem. And a lot of people also write kind of a general conceptual framework to categorize previous research. Like they do like a small literature research, they group papers into different, let's say, common techniques. Like, okay, these papers, they use CNNs, the other papers, they use classical machine learning, these other papers, they use these patterns and so on. So this is more of intellectual work that needs to be done. But all papers need to do a description of the state of the art. And then once you have your literature search and your state of the art, you have to say why is it not sufficient. So this is usually part of the introduction of the related work session. And you should describe why the problem is not solved yet. So you can do this from a theoretical perspective or a practical perspective. And of course, there could be many deficits that you can say, yeah, this doesn't work. For example, if there's low light, it doesn't work in depth images and so on. But you can always describe only the ones that are relevant to this paper. And of course, this is always very important because when you say this is not sufficient, the idea is that when you say this is because you are going to propose a technique or modification, or you are going to do something to address this deficit, right? So this is part of the narrative of your paper. Then what do you propose to do differently? So this is the main content of the paper. So basically you say, here you're describing what you actually propose to the community. You say, okay, you connect it to the deficit. You say the deficit, okay, the deficit is X. And then to solve X, we're going to do Y. And this Y is your technique that you propose. And then this is the main content of the paper, where it describes the proposed technique, the theoretical framework, or research idea and concepts. So usually you first describe the idea as an idea and a concept, and you describe it as in a general way. For this, you use usually figures and text. And later you do the evaluation. And the evaluation is the part where we mention why is it better. So this is the evaluation section of the paper. It can be experimental or theoretical evaluation. And it has the main body of results that argue why the proposed technique is better than the state of the art. And this, of course, means that you need to implement your technique in some framework. You implement some baselines, or use baselines from other authors that are publicly available, evaluate in a data set and obtain metrics, and then argue why is it better. And of course, this connects back to why is it not sufficient. Like the idea is that it's better because you say that the problem has not been solved because of this lack of something. And then your metrics or your evaluation actually measures this exact thing. So for example, a very classical line of papers is that computer vision methods are very slow. They cannot run in real time, for example, in a GPU or in a very fast CPU, and then you want to make it faster. So the why is it not sufficient is, okay, it's too slow for let's say, for real world applications. For example, if you want to do robotics, you should at least have, let's say, 15 to 30 frames per second computation time. And then why is it better? Then you measure, for example, computation time or different metrics related to the computation time, and you compare them. And then the idea is that from this, you can connect back to the why is it not sufficient, saying, okay, we show that our algorithm is faster, and this solves the deficit that we found is the state of the art. And the final W is what is left to be done. And this is the analysis of the results, the conclusions of the future work section. And this also, you need to connect back to your previous questions and basically have a consistent narrative in your paper. So you analyze the results, you find that your method is better than the state of the art, perfect. And then you conclude, okay, in this paper, we presented this technique that solves this problem, which is related to the deficit that you found and why is it not sufficient. And then you also throw ideas on what is left to be done. So for example, you may say, okay, our algorithm works really well, but in your evaluation, you probably always find some drawbacks into the technique or some things that you didn't do, but maybe you wanted to do. And you can put this into conclusions and future work sections. And now going back to the slides is that all of these steps or questions should be present in a paper in a clear writing. Like you don't have to put questions, but you need to identify sections that will answer these questions in a way. And also when I review a paper, I'll always try to to use the same template, which is these 7 questions, 7 Ws, to actually understand what the authors are saying. And after reading a paper, the reviewer should be able to answer these questions to a certain degree. And of course, if anything of these Ws cannot be answered, or basically it's missing, this may point to an issue in the paper. And this is the easiest way to actually find, let's say, mistakes or errors in the paper. Like maybe they didn't actually do a very good analysis of the state of the art, or maybe the metrics they selected are not correct, or maybe they completely forgot to define why the problem is important. And it may sound funny, but actually this stuff happens all the time. All the time I review papers that they are missing one of these Ws. And sometimes they don't say what the problem is important. In other cases, they don't actually describe what they did. Or they describe what they did, but they don't actually describe it in respect of the state of the art. So it's very unclear to see what the authors did compared to the state of the art. And that's a key mistake. So I think these Ws are a very good framework or conceptual framework to actually write and evaluate papers. So you can write pretty much any paper using these 7 Ws. You can write a survey paper, a meta-analysis, a technique paper, a dataset paper, for example, and so on. So now, what is the reviewer's job? Like some people, especially beginners in research, they may be not so familiar with the review process. So here we're going to have a small description of what the reviewer should be doing. And of course, this is how it should be done. It's not necessarily what actually happens in the review process, because it's super noisy, and because of course people evaluate papers, and of course people have varying methodologies and varying, let's say, motivations. So the reviewer should first check that the paper is correctly evaluated, it's correctly written, it is sound, it has a sound methodology, and it's actually understandable. Like this is the first barrier to overcome, that the reviewer actually understands the paper, understands what's the idea behind it, how is it evaluated, what is the methodology, and what is different from the state of the art. And then the reviewer should evaluate and check the claims made in the paper. So usually at the end of the introduction, people make claims like saying our contributions are this and that. And the first thing, I usually go and find this in the introduction and actually check later if these claims are actually correct or not, if I agree with the claims that the authors do, or if I don't agree. Then the reviewer should, as an overall evaluation, should provide constructive feedback that improves the paper. And I think this is super important, because a lot of reviewers, they don't do this. They just say, oh, the paper didn't evaluate against this, then they vote to reject. But the point is not to just point to the, let's say, bad things about the paper or the mistakes that the authors made, but also to how this can be improved. And this is usually the most difficult part of the review process. Because giving constructive feedback, of course, is not that easy, because you need to be a very expert in the field. You need to say, okay, I would have done this in a different way, but you should see if the authors actually can do that, because of course people have different ways to write papers, and you should not try to force them to write a paper in the way you would write it, because it's their paper, not your paper. But in any case, it should be feedback that improves the paper overall. For example, additional baselines that maybe or pointing out which sentences or which paragraphs can be rewritten because they were not clear and why they were not clear. Or maybe improving the notation, improving the figures. For example, I usually look at the figures. If a figure has no legend, maybe you need to find the legend somewhere else, like in the caption. If there's no legend and no caption, and I cannot understand the figure because there's no way to interpret it, then I write in a review, I don't understand this because it's missing a legend or a caption. So this is literally telling the authors to write or rewrite the legend and the caption, and to actually make it clear what is happening in this figure and so on. So sometimes also the reviewers have to evaluate novelty, and I say sometimes because not all conferences ask for this. Maybe in workshops there is less of a threshold for novelty, especially for example in our LXAI and LXCV series of workshops. But in many cases they have to evaluate the novelty of the proposed approach, or what is the gap in the state of the art that is important and needs to be filled. And this is of course more of an opinion, but it should be very clear as well in the review. And if there's a rebuttal process, and this is a process where the authors can see the review before the decision is made and actually reply to the reviewers and say, yeah, this is correct, or no, yeah, this is not correct because we actually did it in the other way. Because there's always the possibility that the reviewer misunderstood the paper, because of course, like we are all people, we can make mistakes. And then the reviewer should ask questions in the rebuttal process, and then interact with the authors and re-evaluate the review if needed. Unfortunately, doesn't always happen because of various reasons, like people maybe write a review and they don't reply after all, or the authors, they don't reply, or even the authors, they also withdraw the paper, say, oh yeah, the reviewers have found a fatal mistake, so they withdraw the paper and then maybe they do new experiments. But in general, if you're a good reviewer, you should make sure to participate in the rebuttal process. Always ask questions, try to interact with the author, especially if your review is very negative. So maybe it can change and reevaluate your review. But also there is research that shows that the reviewers are very reticent, or they don't really change their mind after the rebuttal, or maybe they change it a little, but not much. So that's also, of course, not very good. So here I put a comparison between what the author does and what the reviewers do. So in the left, we have the author, let's say, view, and in the right, we have the reviewer's view. So the author, they draft and design and write the paper. Well, authors, because it could be more than one author, but I mean authors as a general term for all the authors in a paper. And for this, the reviewers provides feedback about the paper. So then the author, they know their own work quite well. Maybe they know it very well, but all of this knowledge is in their minds, it's in their brain, basically. And they work on the paper maybe for a long time, like maybe it can be 6 months of work at least, or even more. But the reviewer usually gives what is called a one-shot look, like maybe they take a few hours to read the paper and then to write the review. And then from this one-shot look, they write the opinion about the work. So of course, this is part of why the reviews are super noisy. I personally, when I review papers, I usually take at least 4 or 5 hours, even if not more, depending on the paper. And this, of course, is because I only review papers that are interesting for myself. And this is how it should work, that the papers you get assigned should be papers that you should be interested. And that's why conferences and journals have this bidding process where you can say, okay, I want to review this paper, this is the paper, and so on. But of course, not all reviewers do this. Maybe one reviewer will put half an hour. So in half an hour, you can barely read the paper, and then they form a very, let's say, noisy opinion about your work. But this is in contrast that the authors, they put a lot of work into the paper, many months of research and time, while the reviewer may only put a few hours. So of course, you need to be aware that maybe you need to put a lot of work into writing the paper to actually convince the reviewer, and you only have kind of one chance in at least for each conference to actually convince the reviewer. And this is a very important, I mean, it's shameful that it has to happen like this, but this is how it is right now, that you may put 1 year of research to do experiments or design an idea, and then a reviewer puts 3 hours only to maybe agree with you or maybe not agree with you. So I think this should be more balanced, for example. So maybe, for example, people can report how long do they take to write the paper or to research, and then this should be proportional to how long the reviewers should take, or how many reviewers there should be there, for example. So also the author, they know their idea in their head, and they try to put it in words, figures, tables in their paper. So this is the way they express the idea in their minds. And the reviewer will try to understand the idea behind the paper, like the idea that is in the brain of the authors, but they will do this only by reading the paper. And that's usually the bottleneck, because you can see that this is kind of an information bottleneck, because you can only put so much information in a paper. And of course, you need to select what information you put in the paper. Usually papers, they say, okay, it's 8 pages limit, 10 pages and so on. And usually there's never enough space. Like in many papers that I write with my co-authors, we usually produce many more results than they can fit in let's say 8 pages. And when you select what is the best result that shows that that is compatible with the narrative, and it's going to be able to convince the reviewers. And the author can also anticipate the reviewer's request or thinking. In general, like if you have a very experienced authors, they can tell you, oh yeah, the reviewer will complain about this, then, or the reviewer will definitely notice this. But the reviewer cannot do this. The reviewer has no way to deal with uncertainty in the paper. So usually, for example, for a conference, if you find a mistake in the paper, you're not sure if the authors will actually fix it in a way that is satisfactory. But for example, in a journal paper, since journals can have multiple review cycles for the same paper, this reviewer uncertainty is much smaller, because then if there's a mistake in the paper, then maybe the authors will fix the mistake, and then you will get the paper again back for review. So as a final thought, I think the author and the reviewer should actually not be enemies, because a lot of people have kind of an antagonist view between authors and reviewers, but it should not be like that. It should be friends. But of course, it's a friend basically, but you don't know the identity of this friend. So it's kind of an anonymous friend. So what is the core advice that I give? Like, this is the advice that you should take from this talk. Well, it's not the end of the talk, of course, you were in the first third, but this is the core advice, is that first, when you write a paper, authors with a lot of experience that usually act as reviewers, they can predict the issues that the reviewers will point out. And of course, you should use this information. Like if you have your professor, for example, your supervisor, or other postdocs, or other collaborators that you have that maybe have many experience or a lot of experience writing and reviewing papers, they can you should definitely try to listen to their advice. And this is why writing a paper alone, especially if you're a beginner, is very, very difficult. Like maybe you have the resources, you have the research, but then putting your ideas into words is not that easy at the beginning. But of course, this improves over time as well. So also another very, very important advice is that always have other, usually more experienced researchers, read your paper and make comments. And this is very, very important to get an outsider's perspective. So maybe you write a paper and then you use a certain notation or certain words, and then your friends or other researchers in your group can read the paper and then can give you some feedback. And they say, yeah, they didn't understand this part. So it's basically kind of a pseudo review of your paper. And this is also very important because once you get this pseudo review, you will actually get the outsider's perspective. And then you can, for sure, improve the paper. And then you can do this in an iterative way as a way to improve the paper. And finally, the very important point of this talk is that other people should actually understand your paper, not just you or your author or the authors. So if other people actually do not understand the paper, then this points to a fatal flaw in the paper or in the way you are writing, maybe the figures and so on. So this is the most common issue pointed by reviewers. Like I reviewed papers where I read the paper and I didn't understand what was the point of the paper. And this may be because I didn't put enough time reading the paper, but it may also be because the paper is not correctly written. And of course, pointing out exactly like you didn't write this thing exactly or correctly, it's much more difficult because it's an overall review or feeling about the paper. Like maybe they didn't answer more than one of the W's I mentioned before. So it's not clear what is the problem, or no, it's not clear why it's not sufficient, for example, and so on. Or maybe the literature search was not done in a correct way, and then they're trying to do something that is already done, because of course all the advances are evaluated against the state of the art. So audience research and audience selection is very, very important. That if you, for example, you have a paper that was rejected from a computer vision conferences, and then you want to submit it to a machine learning conference like NeurIPS, ICLR, or ICML, then you should definitely try to change, because the audience is not the same. Maybe there are less, let's say, computer vision experts. So it's less likely that if you submit a plain machine learning paper, a plain computer vision paper to machine learning conferences, then it's very less likely that you will get an expert reviewer. So maybe you need to rewrite more considering this. And this is, of course, very, very important to consider your audience. So now we go into writing and more into the scientific methodology. So we have some methodological choices that you can do. For example, you have baselines, dataset, and ablations. So baselines, you need to select appropriate baselines. And this is, of course, difficult, but this is a very common source of reviewer complaints. Like for this, you need to know the state of the art very, very well. Like very, very well in terms of even being updated up to, let's say, 3 months in the past. So that's may imply, for example, checking archive to see preprints that maybe try to solve the problem that you're solving, or at least a problem similar, and then use these baselines. And I think the most difficult baselines to select is when you have a new problem where there's not much state of the art, and maybe you need to invent or to come up with some appropriate baselines. And maybe use classical machine learning, some convolutional neural network, something like what practitioners would use, and then you can use this as baseline. But if the baselines are not correctly selected, this is definitely something that the reviewers will complain. But also, you should consider that in many cases, the reviewers will also be people, like they're anonymous, but it's very likely that there will be people working in the same problem, and they may want their method to be used as a baseline for in your paper. It depends on, they may be happy that they see their method in your paper, or if it's not there, then maybe not so happy. So for datasets, you should definitely use the standard dataset for the task. And of course, again, this needs to connect back to the state of the art. If you're solving a task that is well known, then you should definitely use the standard dataset and not try to deviate. If you deviate from the standard dataset, you should definitely justify appropriately why. And this connects back to the 7Ws. Anything that looks, let's say, a bit strange to the reviewers should definitely be justified correctly. And of course, as I mentioned, this can be problematic if in tasks that are new, where there are no available datasets. And you should definitely also consider that if you are working in a new problem where there's no datasets, capturing and labeling a dataset that is also very, very valuable research. And also ablations. Ablations is basically variations of the parameters or algorithmic choices to actually show that your method, let's say, is the best. So for example, you implement a technique and maybe you have one module that does something, and then there's several options for this module. So for example, in faster CNN, which we're going to cover a bit later, you can use different backbone networks, for example. And then, of course, it's not clear which backbone network is best. The only way to select it is to evaluate all of them. Like, you have to evaluate all the possible backbone networks, but you need to select an appropriate set of like backbones that make sense. I know ResNet, maybe the latest networks for ImageNet, maybe BGG, and so on. And this, of course, is a kind of a matter of opinion, but people can help you, like, to say on to agree as a group which ones are the baselines or options that you can choose, and then evaluate all of them. And of course, this means that you need to perform the correct variations of hyperparameters to evaluate your technique and system and find how performance changes and justify your choices. So of course, if you evaluate, let's say, 5 backbone networks for your model, you need to, of course, then use the best. And for that, you need to define a criteria. And there may be multiple criteria as well. So for example, one can be task performance, another can be computational performance. So you can have two let's say, baseline backbones, not one. And all of this needs to be justified with ablations. So we'll come back to ablations later in this talk. Also, how to make comparisons. So also another big source of conflict with reviewers is how comparisons are made. So to start, baselines. So if you have incorrect baselines, like that are not part of CVPR or are very old, maybe if they're more than 1 year old, then some reviewers will complain, especially if the field moves very fast and the computer vision field moves really, really fast. Also, if you have improperly tuned baselines, like you have a baseline, but the baseline has a hyperparameter that you need to tune in your dataset. Especially if you're using a custom dataset, then you definitely should tune the baselines to actually provide the best performance that they can do. And this can create reviewer uncertainty. And by this, I mean that people, if you didn't tune the baselines, they may say that maybe the baseline will improve if you actually tune it. And then this may break your claim of state-of-the-art performance, or at least an improvement of the state-of-the-art. So of course, this is why selecting different baselines and using custom dataset can come with some dangers. So next is train test splits. So this is of course related to machine learning. So you can have what is called leakage between the train and test sets, and you must do all possible to prevent this. Leakage means that you have samples that are in the training set and they're also present in the test set, and this of course makes the evaluation to be unrealistic. Like you will get a much higher metric than you would if you don't have this. So for example, if you create new data set, you should be very, very careful about leakage. So it's very, very important. And also leakage can happen because of individuals being in both sets. Like for example, if you capture data from people, if you have the same person, for example, generate samples for the training set and generate samples for the test set, this will produce leakage. So one way to prevent this is to do a split across individuals. Like you have 10 people and you have 7 people, and all the data points associated to these 7 people or 7 persons go to the training set, and the remaining people go to the test set. So there's no way that an individual is present on both the train and test sets. If you do a data augmentation, you should also do it carefully, because you cannot augment the training set. I cannot augment the test set or the validation set. You can only augment the training set. And I've seen papers where they literally said they augment the whole data set and later they do the train test split, and this leads to leakage. And this happens even at unit submission. So of course, having the right methodology is very important. And finally, if you have an incorrect methodology, like in general, it can also produce leakage. And finally, metrics. You of course, you will evaluate some metrics in your paper. And this must be carefully selected and justified. Like, why are you using this metric and why you are not using another metric? Especially if the reviewers will ask you, while you are not using a specific metric. And a lack of a metric can also lead to a paper being rejected. I mean, I've seen this multiple times. So also you should produce some knowledge by evaluating a metric. Like for example, going back to the sample of computational performance. So of course you need to choose, let's say, computation time, maybe flops or other metrics, or let's say energy versus computational performance, or the cost of operations. Like it depends on what is the narrative in your paper about what metric will be selected. So of course, if you use the incorrect metric for a task, this will be definitely be noticed by the reviewers. So finally, we come to aesthetics and visual appeal. So actually, this is also important because it plays a role on how the reviewers look at the paper, but also the way the paper looks, like the way the figures are placed, the tables, also how the tables are formatted, also plays a role because this makes information much easier to understand. So, for example, if you look at Edward Tuft's books about how to visualize information, there are many, many different kinds of plots, and you should use, let's say, the right kind of plot for the right kind of data that you're using. Like, for example, different comparisons. If you want to compare 3 methods, maybe you may make a standard plot. But for example, if you're plotting points, you need to use a scatter plot. If you're comparing, for example, point clouds, you need to do a 3D plot and maybe tune the view of each point cloud so actually looks good and so on. So all of this actually matters a lot. Not only because of the reviewer will definitely look at it, because other people will look at it. So here are some very basic tips about what to do in this case. So one is to place figures or tables at the top of the page and column, and usually on top, below of these figures and tables, you put text. And the idea is that if you're reading the text, and then from the text you refer to a figure, this figure should be close to the text. And this is, for example, done automatically if you're using LaTeX. But where do you put the figure in the LaTeX code also matters. Like the idea is that it's close and not at the end of the paper, for example. So you should also ensure that the figures images are high resolution and are understandable. Like if they're pixelated, then people will not understand it, or people will be annoyed if you put, for example, pixelated plots. And one common issue is that, for example, if you use matplotlib to produce results, when you export your figure as an image to put it in your paper, you should definitely export it as PDF, or at least as a vector format. Doesn't matter which vector format, but it has to be a vector format and not as a PNG or JPEG file, because PNG and JPEG are raster formats, and they will definitely look pixelated if you print the paper, for example. So you should definitely try to use as much as vector images as possible. And this is almost for free because Matplotlib is a vector library. And then when you save the figure, if you put it .pdf instead of .png, it will save as a PDF that can be integrated into LaTeX directly. So this is something that we all expect because it's so easy to do. Also, you should definitely format tables without vertical lines, with proper spacing and with explainable rows and columns. So I will show you some examples later. But usually you will only have horizontal lines, and you don't have to have horizontal lines for every row. Like you can use these horizontal lines to actually group things visually. And I will show you this later in some examples that I took. And finally, use colors to guide the reader. For example, by highlighting best performing combinations in bold. So this is something that people do a lot. And if you put something in bold, then this will definitely capture the sight or the view of the reader, and of course also the reviewer. But you can also do some more creative things. Like, for example, I've seen papers where they have a table and they have a lot of metrics and a lot of numbers. And of course, they put the best in bold. But for example, they put what are the bad metrics in red color, like they can put the text in red, or you can also put the cell of the table in red. And they put the good metrics that maybe they're not the best, but they're still quite good, in green. And then they change different chases of red and green, depending on how good and how bad it is. And this is very, very nice to see, because then it's much easier to understand the numbers. Because if you present a table with hundreds of numbers, then you need to aid the reader to see, okay, what do you see in these numbers? It should not just be some, let's say, random numbers. So here I have some examples from this deep paper Gestalt from Jiabin Huang. So I have some other examples from himself. So I would definitely recommend to follow him on Twitter, because he is very, very advised about writing papers, graduate school, and so on. But he published this paper in archive about deep paper Gestalt, and what they do, or what he does, is that he gathers a data set of papers that were accepted to top conferences like CVPR, ICCV, and so on. and papers that were rejected, and you train a classifier to discriminate this directly from the image from the paper. And then you can get these class-specific discriminating regions. I think he uses GraphCam, but I'm not sure. So these are for the bad papers, and then you can get some insights about what reviewers think about paper is. So for example, if you look at this part, highlighted now. You look at this part, you see these red areas, and it's a paper that is actually not fitting into the 8 pages. There are 2 pages that are almost empty, and this is like, it's not a reason to reject it, but it's correlated with, let's say, doing improper research or bad research. Like, you should not fill all the 8 pages, but just I usually try to fill all the pages and not have spaces. And this usually means that maybe there's a underlying mistake in the research. It doesn't mean, of course, that the paper is bad, but this is usually what reviewers they look like. And you can see, for example, here, they also looks at the figures. So of course, if the figures, for example, cannot be understood, they're not understandable, then you should this will definitely lead to rejections. And it also looks, for example, in this case, to the lack of what we call the summary figure that usually people put at the first or the second page. And in these papers, there's no figure like this. So the thing is that these results, they don't mean that the paper is actually bad research, but it may point that the paper shows that it's not correctly written or it's not understandable. And that's very bad, because if people don't understand your ideas or the significance of the results, then they will probably vote to reject. Like, this should be very clear from the paper, and this is something you can control as an author. So these were the bad papers, and here I have the good papers. So the same methodology. So you can see that it's again looking at the first page, but in the first page now there's a figure that shows like the basic core idea of the paper. And this is in all of these top papers. And it also looks at the figures. And as you see, all of these papers, they fill all the pages, all the 8 or maybe 10 pages in the paper, in the maximum. So they fill the whole, let's say, maximum number of pages. And they also, it looks like at the figures. And so making, let's say, a good narrative, good figures and good tables is very, very important to get your paper accepted. And it's usually it's also a very good service for your own peers, for other authors and potential readers. Like, if your paper is very easy to read and you clearly get the idea from the paper, then this paper will probably be highly cited and maybe will make a good impact in your career. So now we come back to what I mentioned, this teaser figure on page 1 or page 2. So usually the figure 1 in a paper. So many people, they put a specially crafted figure or diagram that teases or explains the proposed technique and how is it different from the state of the art. So this helps explain in simple words diagrams what the paper is about and how is it different from the state of the art. So I think this is a very good practice. So I got this figure from Dabowski and Gal. So it's a paper about explainable AI. So this is the figure 1, which is I think is in page 2. And you can clearly see, okay, this is the input image, this is the saliency map. And you can clearly see from the results, okay, maybe this is very clearly explaining why a cat or a dog is classified. And then you have a caption that explains this concept very clearly. So when you read the paper and then you flip to page 2, you will, if the first thing you will see is this figure. And then from then you will maybe get a clear idea that will actually influence how you read the rest of the paper. So also toy examples. So this is related to the concept of the teaser figure. So many papers also include examples or, let's say, concepts on small or toy datasets in order to showcase the basics of the idea/concept. So this connects back to the teaser figure, and it gives the reader a small idea of the basic concept in the paper. And of course, you can have more complex examples later, but at the beginning of the paper, you should definitely try to do this. So I make this figure myself because I work in a certain team in machine learning. So I take the 2 months dataset, which comes from scikit-learn, and I evaluated a bunch of uncertainty methods. And I'm writing a paper like showing what are the differences between these methods. And then by this figure, you can clearly see that first, that many methods, they do very similar things, but at the same time, they're different. For example, this gradient here and this DUQ here, it works in a different way than the other methods. And you can see that, for example, that dropout and drop connect, they produce different uncertainty. So this is kind of a figure that I used to introduce the concept of uncertainty in machine learning and in computer vision. So people actually understand me what I mean. So uncertainty here is that if you see in yellow, it's like highly uncertain, and usually this region between the two data is highly uncertain, because if one point is very close to this line, it depends if you because all of these points can be noisy. So if you move it a little, it will be classified as one class, and if you move it to the other side, it will be classified as the other class. While a point that is very far from this line will be clearly classified as one of the. So this is one example of a figure that I am making to show the idea for one of the papers I'm writing. And this is, of course, a toy example, because later I have evaluations, for example, in Cipher 10 on fashion MNIST and so on, and these are like the main results. But I use this small toy example to actually show to the reader and to the reviewers that this is like a very basic concept of what they should be seeing later. So now I start with Jiabin Huang advice. So I took it from this Twitter thread. So he provided like 10 different figures about what to do and what not to do. So I thought it's much better to actually include his figures instead of trying to make the same idea. But I will have to put my own figures. But this is usually very nice figures. So I have, I think, 5 slides about this. So this will probably go faster than the previous slides. So for example, the first thing not to do, you need to make an appropriate caption that guides the reader about what to see in every figure and in every table. Not just say, okay, these are the results for this data set, but then you can write a bit more, like what does it mean, what are the best, what to see in these numbers and so on. So what not to do, just write like, please refer to text for detail. And what to do, you have a figure, and then you put appropriate captions to each of the images, like these ones here. And then you write a several line caption to the whole image, showing how these results they relate to your narrative. Also, you should always include citations in the text of the paper to guide the reader to which technique/data is being compared. So for example, you read this, we compare to A, B, and C. If you don't know what A, B, and C are, then of course, that's not a very good writing, but it's very easy to add references, which they don't add much space, but it's very clear to which paper you are referring. And this is super important because sometimes I read a paper and they evaluate it on whatever data set. And maybe if it's not a very well-known data set, I try to find, okay, what is the reference to the original data set? And I cannot find it in the paper. And then I get super annoyed because it's not clear actually which data set is being evaluated. And this is even more important when there's several variations of a data set. Like for example, Cipher 10 has like 5 or 6 variations. MNIST has hundreds of variations, like there's fashion MNIST, there is e-MNIST, there is non-MNIST, and there is a lot of datasets, and it's very easy to get confused on which MNIST you're using. So the next is to use a consistent notation and use it in your figures or tables. So you look at this, where's the mouse here? To this figure here. So it's a really nice figure. Like it shows the process technique, maybe it's contrastive loss, adversarial loss, and so on. But you see they use colors for something, like they use blue, some shades of blue and some shades of green, and these are used for something. But it's much better if you actually include a caption pointing out exactly what each of these things are. For example, here they use blue and green for the Y and X domain. The yellow things are losses. The red things are prior distributions. And some symbols are, for example, encoders, decoders, and generators. So by doing this, it's much, much easier to actually read your figure, because maybe I can understand it if I read the text, but then you should try to aid the reader about how to do this. So also you should try to make it easier for the reader to interpret your figures. And I think Jiabin, what he said is that don't make people play to make a correspondence problem. Like for example, you look at this figure, you have a lot of rows and a lot of columns, and it's not clear what each of them mean. So if you look at here, then you actually add text to the beginning of the rows and text to each of the columns to actually indicate, okay, to each indicate, for example, okay, the columns are different methods, like at the end, it's ours. And I think it's very important to mention which is your, let's say, your technique, because sometimes people forget about that as well. And then they have different references to indicate, okay, these are the results produced by this other paper and so on. And then in the columns, they have different metrics or different images, and each of them has a different meaning. And then by doing this, it is much easier to understand the figure. Also, for equations, you should definitely try to use human readable notations. Like, for example, if you use 1, 2, or it is okay in terms of mathematics, but it's not so understandable. But if you replace it, for example, by L total or lambda rec or lambda smooth, it's much easier to actually understand. So you see, this maybe sound silly, or it's actually not so common. Like most of the top published papers, they do it, but when you begin writing papers, this is not so obvious. And also group captions in subfigures and tables for easy interpretation. Like instead of just putting a general caption that automatically comes with LaTeX, you should definitely try to group them. So for example, okay, the first is the input, and you actually say that this is the input. Then the second, maybe the two second and third columns, they're related, and this is novel view synthesis. And the last two columns are FOV manipulation. So this is much more clear if you actually include this in the figure and also in the caption, because sometimes this is only provided in the caption, and this makes it a bit difficult to understand. So you can also augment the mathematical notation in your text with a human interpretation. So you say f of f sub theta takes I and ij as inputs and blah blah blah. It's much easier if you write the flow estimation network f theta takes a pair of frames I, j, and I as inputs and produces a dense flow field wi towards j. So this also may sound silly, but it's much easier to read once you relate, for example, the concept in your paper with your mathematical notation, and you do this over and over. There's no problem by repeating itself, because then if you don't do this, then people have to play the correspondence problem, try to find out, okay, what was f of theta, and especially if you have several networks in your model, then it's each of them should have, of course, a different letter or different notation, but it's very easy to get confused with each other. Also, you can use the image and shape attributes to describe ideas. So for example, here, they have the object detection results, like some bounding boxes, and then they have some other attributes that they output, but these are plotted without the image. But if you put the image as a background for these results, and you use some alpha blending, or you just decrease the saturation of the image, then you can definitely, it's much easier to actually relate this, especially. So this is also very important for computer vision papers, because they usually present a lot of visual results. Also, you need to provide details between differences in the SOTA and your proposed method. Like you can do this. This is a very standard table that compares your method with state of the art, with Snorla's, Bulbasaur, and Psyduck. But if you actually go back to your state of the art or your literature search, and you have this conceptual framework of how these methods differ, like some methods to use external data, some of them are fine-tuned and so on, and you put this in the table, it's much easier to understand. And here it's much easier to actually understand the contribution. So for example, from the first table, so actually I don't know from which paper this comes from, or where the numbers are coming from, but I can immediately from the second table here, you can actually understand that the idea of the paper is that you do the same evaluation or the same performance, but you get higher MAP, but you don't need external data and you don't need fine-tuning, and that's usually better. And I'm doing this only by looking at a single figure of the paper, and that's the power of when you make a very good figure or tables for your papers. So also you should have one message or ablation per table. So you should not try to crowd the tables with all the results in one table. You can divide this into multiple tables, and you can even put them in multiple columns to use the same space. So you just definitely try to do something, not do something like this and do something like this. And of course, in the method, you should definitely try to describe and connect what are the differences between these methods to actually guide the reader. So I think this is one of the last one, is to format and group table columns in a human understandable way, especially when you use related metrics and datasets. So here you see that in these tables, there are no vertical lines, there are only horizontal lines. And there are many metrics like absolute relation error and so on. And one way to present this is to actually put, for example, here, a small hint that the depth is an error metric from the depth image, for example. And then you include this arrow indicating that lower is better. And then here you have depth, but you have an accuracy, and then higher is better. And this is, of course, much easier to interpret for the reader. And here you can also have pause, for example, error metric. You can also point that this is better when it decreases. And this is even more important when you have these metrics that they have different meanings if they're lower or higher. So this is also a very easy way to guide the reader. So yeah, now we're close to the end. So also we shared Ross Girsch's advice from ICCV 2019, 2 years ago in South Korea. So I saw this, I didn't attend this talk. I saw it through Twitter in this link that I'm showing around here. So this is mostly about object detection. So here I put the ideas of Ross in the slides. So these of course are not my ideas, but this is very good general advice. So the first is that a paper should be about a single focused idea or question. You should not try to answer many things into a single paper. An idea usually means a method. And what should I learn from this paper? So you should learn what condition does it work, like in which data set or in general conditions, when it does not work, if the idea has multiple components, which are the most important, and what implementation these are important. And as I mentioned, this is specific to object detection, but I think these ideas, you can see that they're very general. They apply also to many other techniques and even to other kinds of papers. So in general, reviewers and also other authors, they may not really care if your idea is plus some unrelated ideas or tricks leads to state-of-the-art results. So what usually they want is to actually learn interesting things about your idea, or to actually want to learn your idea and see how it can be implemented in their own paper. So about simplicity, like this is the most basic way how to make evaluation. You start from a solid baseline method. Like for example, object detection, you take the latest of the detection method, you apply your ideas to it, and then you perform ablations under simple settings to actually see what parts of your idea are actually the ones that matter for performance. And this is usually as I mentioned, the most basic or important evaluation method for any paper that proposes new methods and techniques, which I think are probably the majority of the papers that are submitted to these conferences. Also about ablations, that you should definitely support all your claims. Like every time that you claim something in your paper, you should support it by citation or by experiments. Like you say, okay, our method is better than X or Y, and then you say this is because in table whatever you showed the results and MAP is larger, for example. It may sound obvious, but you need to write this. You always need to write claims in your paper. If you cannot support all the claims, you can qualify the statement. For example, instead of intuitively increasing X is important for Y. Like if there's no citation or this is obvious, you can put it that is intuitive. Or increasing X might lead to improve Y. This may, it's a key part of this sentence. That it may or may not, but we think that, or we try to think that it may or not. Like usually arguing things that are obvious or intuitive is, I think, the most difficult, because for the stuff that is not obvious or not intuitive, you can either do an experiment to actually ground the claim, or you can cite other papers. But usually if something is intuitive, then maybe it's not citable, or no one has done something like this, then you need to explain this. Why is it intuitive and so on? Oops, oh, it's duplicated. So yeah, sorry, small mistake. So now here I show you the ablation tables for mass RCNN. So I took this directly from the mass RCNN paper. And so you see first is that they actually do, for one table, they have only one concept that they're basically explaining, or one idea. So for example, here in this table A, they actually evaluate the backbone architecture only. In table B, they actually evaluate if it's better to use a soft mask or a sigmoid mask. In table C, they evaluate if it's better to do this ROI align or other ROI region of interest pooling. And here they evaluate, for example, in table D, they evaluate different metrics of the best pooling methods. And you see here in table C, they have these checkboxes to show what are the differences between these methods, like what kind of aggregation they use here. Match pooling or average pooling, if it's aligning, if it's bilinear interpolation, and so on. So see, there's a lot of information only in the tables, and this of course means that you should definitely try to add as much information as possible. So yeah, we think we're close to the end of this tutorial, at least the practical part, or at least the talk. So one point that we also need to take into consideration is that there's a lot of reviewer uncertainty and variability. like you as authors, you definitely need to be aware that in most top conferences, there's a significant variability in reviewer because, well, there's a variability in reviewer opinion, experience of the reviewers, and attention of the reviewers. Like there's many PhD students that maybe are reviewing papers, and I don't think there's anything wrong with that. But of course, maybe they don't have the full view of the state of the art or full connection with other topics. And this is because there's a severe expert reviewer shortage. So what happens is that, of course, the number of papers is continually increasing, but the number of reviewers is not increasing as fast as the number of papers. And also many good reviewers, they become area chairs. And by becoming area chairs, they don't actually review papers. They review the reviews made by other people and then make the decisions, whether to accept or reject a paper. And finding good reviewers is not that easy. It's difficult. And I think this also means that the conferences should tap into additional sources of reviewers. For example, many conferences, they say, if you publish a paper in our conference, like if you get a paper accepted, then you may review for the next conference, or they may invite you, but maybe this is too restrictive. Like, for example, I think NeurIPS had this not sure if constraint or at least this was the idea, but I got a review request from NeurIPS for this year, and I have not published a paper in NeurIPS. So I think basically they actually noticed me from reviewing from other machine learning conferences, because of course the reviewers for many conferences are shared. There are many people that are reviewed for multiple conferences. So yeah, as I mentioned, the deluge of new papers being submitted to each conference. And also this is very annoying from the author's perspective. Like you put 6 months of work to write a paper, and then someone puts 2 hours to read it and then doesn't understand the idea and then rejects your idea because of some misunderstanding. And of course, all people that do reviews should remember that it's not only about the decision, but also about how to improve the paper, how to improve the research, like maybe throwing some ideas into the air, do some brainstorming, and how to improve the paper. So the idea is that the authors, they get something also as well, that, okay, yeah, the paper is rejected, but if we make these changes, it has a chance to be accepted in another conference. So this is super important. And I think a lot of reviewers, they actually forget about this. So I think the only possible solution for this problem is to invest more resources, which usually means time, into the review process and to train reviewers. So at our LXCV CVPR workshop, we actually did this. We trained some of the reviewers. We did a reviewer webinar, and we had a reviewer mentoring program. I think it was quite successful to actually improve the reviewer pool. So one final slide about research ideas in computer vision, machine learning, and artificial intelligence. Because also part of writing papers is, of course, selecting the idea. So of course, if you can write the best paper in terms of writing, but if the idea is not interesting, then it's very likely that people will accept it. So of course, you should definitely work or research on interesting topics and try to find your own niche. And you should definitely consider the societal and research field impact of your problem when you select problems. So for example, you have a problem that is not important. When you solve it, only a few people will care. But if it's a very important problem, even if you have a small progress, it will have a large impact and a large importance. So for example, try to solve, well, you don't have to solve, but you want to work in the direction of solving a very big problem. So for example, climate change, poverty, for example, fake news and misinformation, and so on. I think even if you do a small step, still it's a huge problem. And I think this will probably bring a lot of attention to your research and to your papers. And I noticed for a personal experience that for my PhD, I work on marine debris detection, which I think is a very important problem. And then I started seeing a lot of people citing my papers, and even projects like funders were funding projects related to this research to say, oh yeah, this is actually an important problem. And yeah, so if you don't work in an important problem, then of course, not many people will care. Like if you work maybe in a very, very niche problem in computer vision, maybe a problem that even has been solved already, then of course that's not so good. So selection of problems also is a very important part of let's say writing papers, because in the end you select a paper, a problem, you will definitely select or write papers later. So you definitely also consider the impact of AI developments on minorities and disadvantaged groups. And I think this is most important for us, that we are a minority in the LXAI community. So for example, don't try to develop algorithms that can be used for racist ideas or for discrimination, for example, and so on. So in terms of, for example, big societal problems, I think one I mentioned how to detect, for example, corruption in general, like for example, corruption in documents or like the concept of corruption. It's of course corrupting society, and it's a very bad thing, especially in Latin America. So how can you use artificial intelligence to detect this? I think if you make a small impact or a small step on this, it will be super impactful in the future. Also think very deeply on who gets powered by an algorithm, and always think and try to prevent misuse. So for example, a lot of people that work in fairness in AI, I think they're working in a very important field. Even if it's very slow to move, doesn't matter because it's a very important problem. Also, just improving on the state of the art, like a percentage on vendors, is not always the best. New problems, tasks, and datasets are also very, very important. I think, like for example, if you're doing a PhD, you don't have to work in improving some state of the art because that's also difficult. It's uncertain, but you can also work in new problems, like propose new data sets, new tasks that can be solved by other people, and then you do your own evaluation and so on. I think this is also super important. So some take-home messages. So writing papers is an art. So it also requires some artistic skills, not just scientific skills, to clearly present ideas. And of course, this usually no one is born with this. So this is something you develop over time. So the ideas of this tutorial is for you to get some very clear ideas of how you can do this. And I think the best way to do it is to write papers and try to get them published, and also to try to get feedback about your papers from other people. So not forget that we write papers so other people can actually understand them and they have a clear audience, and to advance the state of the art. But of course, the important idea is that always other people have to understand your paper. If other people don't understand your paper, that's super bad. And means that you need to change what you're doing. And also writing, presenting ideas, data, figures is not as easy as one might think, and clarity is paramount. Like for example, if you're in a PhD program, they usually provide soft skill courses about how to present ideas, how to make presentations, how to present data and figures. And I think this is also very important, that will definitely also improve your skills and the way you write papers. Also, it takes time and / experience to polish a paper. It's just not about the evaluation results, but how they're presented. And this is very important to be aware that even if you have the best results, if you don't communicate them correctly, then it's very unlikely that other people will understand it. So what I usually do as a final takeaway message is that I look at highly cited papers to see how they present results, how they do tables, how to do formatting, how to do figures. And of course, I imitate them. Like I got some very nice ideas of, oh, this was very clearly presented. Maybe I can use this idea or this way to present data or figures in my own papers. And I think this has time that has been very well spent. So here I share some writing and reviewing resources. So of course, there are many workshops that have happened in the past. Like for example, this Good Citizen of CVPR, or the CVPR 2020 tutorial on how to write a good review. And you can find these links in, I will put the presentation in my website. And there's also this paper about how to write a good CVPR submission by Bill Freeman. So all of them, they are basically a treasure trove for how to write good papers. So yeah, so thank you for listening to my tutorial. It was a bit longer than I expected. So before I go into questions, so let me check if there are questions in the chat. Okay, not yet. I will actually show you some papers and dissect them related to what I actually mentioned in the talk. So you can already start writing questions in the chat. But for example, we can start with the mass carcinoma paper. So you can see it here. So you read the paper, and the first thing you see is this figure. And this figure basically is a conceptual, let's say, framework of how mass carcinoma works. And it's right there in the first page. So this is the first thing that you see. And as you move forward, in the second figure, you have already some results on the COCO test set, and then you can see, okay, yeah, it works really well just by looking at these figures. Then you have some more tests, and then, for example, here you have the related work, and then you have these titles here. You see here, instance segmentation here. So this is a way to group text inside, like it's a way to group paragraphs. And if you go there, then mass carcinoma, and then they also have these kind of paragraph titles, and I usually write them in bold. So they stand out from the text. And then by doing this, it's much easier to read your paper and basically to navigate in the text. So for example, here, okay, network architecture, the head architecture, and there's a figure about it. implementation details, how to do training. So you can clearly see here that here they describe how to do training, and you don't have to read the whole paper to find out this. Here's how to do inference and so on. Then the experiments, for instance, segmentation and the results. And here are the tables I mentioned before. So it's a very nicely written paper, but it's not only a very nice written paper, but also the technique. It got a best paper award, I think, in ICCV 2017, if I remember correctly. And it was because it works really well as well. Now I'm going to show you another paper, but this is not an actual, it's kind of a graphics/computer vision paper. So this is published at the Transactions on Graphics of the ACM. So I will show you because they also use a slightly different format. And you see, okay, we have the authors, the title, and also again a direct figure that shows some initial results right in the beginning of the paper. They show this is the input image, and these are images rendered by their own method. And basically, what they do is to do relighting of an image. Like you have a photo of a person, and then you can see how the photo will look like with different illuminations. And this is, of course, completely rendered using an algorithm. And then you see in the second page, they have this takeaway or spoiler figure, how it works. Then they have tried the work. They also have these titles to separate different parts of the paper. And they also have this showing of their dataset. The architecture, and you see that all the captions, they have at least 2 or 3 lines of text. The evaluation related images, they also use this nice mathematical notation that I mentioned there. And then they have the algorithm, and I really like this table here. You see it here. That they have numbers, but they use color coding to see, okay, what is the best number and what are the worst numbers using in colors. And you can find the top 3 uniques for each metric are highlighted in red, orange, and yellow. And you see, this is much clearer to see than just finding the numbers. And here they have some validation results. And I think they also have some failure results. Yeah, and here they use the same. And to finish, I will show you one paper from Yabing's Huang's group, which I also really like because, of course, I was thinking if he makes so much advice, he probably applies this advice to his own papers, right? So, of course, then you see the first figure. Again, is this teaser figure. And this is a really nice, figure here. Because here they show what is their architecture, and they also show in a graphical way what are the other architectures that they use in state of the art. So you can visually see what is the difference between their paper, and you can see this right in page number 2. So yeah, we can also see here they have a comparison of different methods. So it's basically a way to describe the state of the art as a table. So different reconstruction, loss functions, and so on. What else? Yeah, results. And then you see they use color coding here for different things. So this color is there for something. They use this again these ticks to indicate how the variations are different in the state of the art and so on. And they have many results here altogether. So I think now with this, I can take some questions if anyone has questions. Yeah, so I see here one in the chat.
Well, in the chat, I think it's only observation about EP's figure for data visualization.
Yes, definitely. Yes. So anyone has questions? You can also unmute yourself and then ask questions.
Hi, Matias. Yeah, thank you. I have a question. Yes, thank you very much. It was a great presentation. And yeah, I think that, something that I have a question around is like that, like how we actually train this, like that teaser figure that, like that main figure that it is at the beginning, that it is actually not related to the, like it is related to the research, but which did not come out from the results. Like we just make it out to make it like nice and clear. So because I really think, as as you were presenting, that in general, like people start the review process, they read the title, they see that first figure, and that will give some bias in all the reading of the paper. So like kind of making out with the title and that main figure is kind of a bit of the art. And so how, like, I don't know, like, what would be like the main tips, like when kind of working on that figure? Like you will do at the end of the paper, you will do before starting the paper to have like an idea of how you're going to write the full paper, or on you know, how you get the you know, like the actually drawing process. Like you prefer to do it in, like, in a specific software. I don't know, just tips on that kind of like main figure.
Yeah, sure. So I think this can be done either at the beginning of the paper or at the end, but it depends, like if you have a clear idea about this concept. So it doesn't matter when you write it. But in terms of software, I think people use like vector graphic software, like for example, Inkscape or Draw.io or VCO, for example. Any software that you can use to draw diagrams, you can use it for this. So they will close it in 3 minutes. So you can also use, for example, ticks in LaTeX to make some diagrams, and this also. So it's more about personal opinion or preference. But of course, there are many software packages that you can use for this. Like I think most people use Draw.io, they use Google Drawings or Inkscape for this. But of course, you need to learn to use this software. But I think it's very profitable to actually do this. Like I printed a ticks book, like the ticks tutorial, and I started reading it, and I found many things that are very useful to actually make this kind of figures. So definitely it's a skill that needs to be learned. Like I think I'm not the best to do this, but I think also you can find in Twitter many examples of these figures. Like there was a thread that I saw in Twitter recently about like what figure one of a paper do you like, and then you can get ideas from this. So try to also to get these figures from other papers. Like if you like the way they do it, you can also apply the same idea for your own figures, right? Like no one owns these figures basically in terms of intellectual property.
Yeah, that's great. Thank you very much, Matias.
Welcome.
Matias, we have another question. Let's say, what about the order of the authors in a paper?
Oh,
from
yeah,
the author's perspective?
That's difficult because
question, I think.
Yes, that's a tough question because usually what happens is that this should be defined before the paper is written. Like it should be proportional, like to the importance of an author. Like the author that writes the paper that does most of the experiments should go at the beginning, and the author that supervises most of the work should go at the end, for example. But of course, this depends on the field. Like in computer vision, there is this I mean, for example, in mathematics, they always write the authors in an alphabetical way. So the first author doesn't have a meaning that we have. So this is very field dependent. It's more of a cultural thing. So yeah, so another question is how you mentioned capturing level and new datasets. So the thing is that if you make a new dataset, you can also make a paper about the dataset itself only. Okay, we have 1 minute, so we try to answer them fast. How deep should we? Yeah, so I was mentioning that there are dataset papers. So you can try to find dataset papers, like for example, the ImageNet paper, Coco, for example, has a dataset paper, and then you see how to describe a dataset. How deep should I go in the description of a well-known algorithm? Well, you can. It depends on the technique. Like maybe you don't have to go very in detail, but if it's very important for your technique, like for example, if you're modifying it, then maybe you should describe it in a lot of detail. But if you're only using it as a baseline, then you don't have to describe it. You can only refer to in a citation. And high-level methods, yes, you should definitely say how you select them. Yes, that's what I mentioned here.